The Earth is getting crowded. Today we share this world with over 8 billion people. By the year 2050, our numbers could swell to nearly 10 billion. That is almost 2 billion more mouths to feed. To meet this challenge, we must produce somewhere between 60 to 70% more food than we did just a few years ago. This is not a small task. It is one of the greatest challenges humanity has ever faced. We must find a way to nourish every person on this planet, from the bustling cities to the remote villages, without asking for more than the Earth can give. Our current methods are already straining the system. Agriculture is a thirsty endeavor. It drinks up about 70% of all the fresh water we use. Farming also takes up a vast amount of space. It currently occupies nearly half of the planet's habitable land, a footprint that has displaced countless ecosystems. Furthermore, our food system contributes significantly to climate change. From clearing land to powering tractors and producing fertilizers, it generates up to 1/3 of all human-caused greenhouse gases. We are standing at a crossroads. We cannot simply scale up our existing practices. Doing more of the same will only push our planet's life support systems past their breaking point. The problem is not just about quantity. It is also about resilience. Our climate is changing. We see more frequent and intense droughts, floods, and heat waves. These extreme weather events can devastate harvests, creating instability and threatening the livelihoods of millions of farmers. New pests and diseases are emerging and spreading to new regions, challenging crops that have no natural defense. We need our food supply to be not only bigger, but also stronger and more adaptable. We need crops that can withstand the stresses of a warmer world. We need farming methods that protect our soil, conserve our water, and heal our climate. So, the challenge is clear. We must innovate. We need to produce vastly more food. We must do it using less land and less water. We must do it while drastically reducing our carbon footprint. And we must do it in a way that helps farmers, big and small, adapt to an unpredictable future. This requires more than just incremental improvements. It demands a revolutionary leap in how we understand and manipulate the building blocks of life and the environment. It calls for a new tool, a new perspective, a new way of calculating our path forward. The answer may lie in a realm that seems far from the farm, the strange and powerful world of quantum mechanics. We are living in an age of incredible technological advancement. Modern farms are not the simple fields of the past. They are complex operations powered by data and precision. Farmers use GPS-guided tractors that plant seeds with centimeter-level accuracy. They deploy drones that survey fields and identify areas of stress. They rely on sensors that monitor soil moisture and nutrient levels in real time. Artificial intelligence helps analyze this flood of data, offering recommendations to optimize water usage, offering recommendations to reduce fertilizer application, and offering recommendations to improve crop yields. These tools have made farming more efficient and productive than ever before. They represent the peak of what we can achieve with today's computers. However, even our most powerful supercomputers have limits. They operate on a simple binary principle. Bits of information are either a 0 or a 1. By stringing together billions of these bits and processing them at incredible speeds, they can perform amazing feats of calculation. But some problems in nature are not simple or linear. They are fantastically complex, with an astronomical number of interacting variables. For these problems, a classical computer, no matter how fast, hits a computational wall. It's like trying to map every grain of sand on a beach by counting them one by one. You will eventually run out of time. One such problem is simulating molecules with absolute precision. The world of atoms and electrons is governed by the bizarre rules of quantum mechanics, where particles can exist in multiple states at once. To break through the computational wall, we need a new kind of computer. We need a machine that thinks less like a light switch, which is either on or off, and more like a dimmer switch, which can be at any point in between and many points at once. This is the essence of quantum computing. It harnesses the strange principles of quantum mechanics, the laws that govern atoms and subatomic particles. Instead of classical bits that are 0 or 1, quantum computers use qubits. A qubit is a game changer. The magic lies in two phenomena: superposition and entanglement. Superposition means a qubit can be a 0, a 1, or both at the same time. Think of a spinning coin. In the air, it's neither heads nor tails. A blend of both. A qubit holds that blend until measured. That lets a quantum computer explore vast numbers of potential solutions at once. With a few hundred qubits, it can process more information than atoms in the known universe. This is parallelism classical computers can only dream of. The second key principle is entanglement. Einstein called it spooky action at a distance. When two qubits are entangled, their fates become linked, no matter how far apart. One of the most energy-intensive processes on Earth is the creation of fertilizer. Modern agriculture heavily relies on the Haber-Bosch process, an industrial method invented over a century ago to produce ammonia, a key source of nitrogen for crops. This process is a brute force solution. It requires immense pressures and scorching temperatures around 450 degrees Celsius to force nitrogen from the air to react with hydrogen. While it has enabled us to feed billions, it comes at a steep environmental cost. The Haber-Bosch process alone consumes 1 to 2% of the world's total energy supply and is responsible for a staggering 2 to 3% of global carbon dioxide emissions. Nature, however, has a much more elegant solution. Certain bacteria living in the soil or on the roots of plants like soybeans can also convert nitrogen from the air into ammonia. They do this using a complex enzyme called nitrogenase. This natural process happens at room temperature and normal pressure, with no fossil fuels required. The secret lies within the intricate atomic structure of the enzyme's active site, a cluster of iron atoms and molybdenum atoms. For decades, scientists have dreamed of replicating this natural efficiency. The problem is that the quantum mechanical interactions within this molecule are so complex that no classical computer can accurately simulate them. This is where a quantum computer can change everything. By its very nature, a quantum computer is perfectly suited to simulate the quantum behavior of molecules. It can model the exact positions and energy states of every electron within the nitrogenase enzyme. This allows scientists to watch for the first time exactly how nature breaks the powerful triple bond of nitrogen molecules. The art and science of plant breeding have given us the high-yielding crops that form the backbone of our global food supply. But the traditional process is slow and methodical. It involves cross-pollinating plants with desirable traits and then growing out generation after generation of offspring, carefully observing them in the field to see which ones inherited the right combination of genes. Finding a new variety of corn that can tolerate drought or a new strain of rice that can resist a bacterial blight can take a decade or more of patient work. In a world where the climate and an array of pests are changing faster than ever, we do not have the luxury of time. Modern genetics has accelerated this process. Scientists can now sequence a plant's entire genome, its complete set of genetic instructions. They can use tools like CRISPR to make precise edits to a plant's DNA. However, the sheer scale of the genetic data is a major bottleneck. The genome of bread wheat, for instance, is 5 times larger than the human genome. Identifying the complex interplay of thousands of genes responsible for a trait like yield or heat tolerance is an immense computational challenge. A classical computer can search for simple correlations, but it struggles to model the complex, multi-gene interactions that govern most important agricultural traits. Quantum computing offers a way to supercharge this discovery process. A category of algorithms known as quantum machine learning is especially well suited for finding subtle patterns in massive, complex datasets. A quantum computer could analyze the genomes of thousands of different plant varieties. Every farmer is, at heart, a risk manager. Their success for an entire year depends on a series of critical decisions made under conditions of uncertainty. When is the best time to plant? How much irrigation will be needed? When is the optimal moment to harvest? These decisions are all profoundly influenced by the weather. An unexpected late frost, a prolonged heat wave, or a sudden hailstorm can wipe out a crop and a farmer's income. While modern weather forecasting is a marvel of science, its accuracy decreases significantly over longer timescales and smaller geographic areas. A regional forecast might predict a 30% chance of rain, but it cannot tell a specific farmer if their particular field will get it. The challenge lies in the chaotic nature of weather and climate systems. These systems involve an immense number of interacting variables: temperature and pressure gradients in the atmosphere, soil moisture, evapotranspiration from plants on the ground. Classical climate models are incredibly complex, yet they rely on approximations to be computationally feasible. They divide the world into a grid, and the processes within each grid cell are averaged out. This approach is good for predicting large-scale, long-term trends, but struggles to capture the fine-grained, local dynamics that matter most for agricultural planning. Quantum computers can handle this complexity in a fundamentally new way. Their ability to process a vast number of variables and their interactions simultaneously makes them ideal for modeling complex systems like the climate. The image of a quantum computer is often one of a massive, complex machine housed in a highly specialized laboratory, cooled to temperatures colder than outer space, tended to by a team of PhD physicists. This is largely accurate. For the foreseeable future, quantum computers will be large, extraordinarily expensive, and far too delicate to ever sit in a farmer's barn or a local co-op office. This reality might suggest that quantum farming will be a tool only for the largest, wealthiest agricultural corporations, potentially widening the technology gap with smallholder farmers. However, a different model has already transformed our world: the cloud. We no longer need to own massive servers to store our photos or run complex software. We simply access that power remotely through the internet. The same model is emerging for quantum computing. Major tech companies are already building quantum computers and offering them as cloud services. A scientist or developer can write code, send it to a quantum processor thousands of miles away, and get results back on their laptop in minutes. This cloud-based approach is the key to democratizing quantum agriculture. A smallholder farmer won't need to understand quantum mechanics or own a multi-million-dollar machine. They will only need a network connection, perhaps a simple smartphone or a tablet from an extension service. Complex quantum calculations will run in remote data centers. Designing a new biocatalyst, identifying the best seed variety for local conditions, generating a hyperlocal seasonal forecast. The results arrive as clear, actionable advice. Plant this variety next week. Apply 20% less water for the next 2 weeks. This model can also revolutionize agricultural supply chains. While the promise of quantum farming is immense, we must approach this future with a healthy dose of realism. The road from today's early-stage quantum processors to a world of quantum-enhanced agriculture is long and filled with significant challenges. This technology is not a magic bullet. The first major hurdle is technical. Today's quantum computers are still in their infancy. They are noisy. Vibrations, temperature fluctuations, other environmental interference, which leads to errors in their calculations. Building larger, more stable, and error-corrected quantum computers is a monumental engineering and scientific challenge that will require years of sustained research and development. The second challenge is the high cost. Building and maintaining a quantum computer requires billions of dollars in investment. While cloud access will make the technology more accessible, the service itself will still be expensive, at least initially. Who will pay for this? If the cost is passed down to farmers, it could become a luxury that only the wealthiest can afford, exacerbating inequality. We must develop business models and public-private partnerships that ensure the benefits of quantum agriculture, such as better seeds and forecasts, are affordable and accessible to all. The challenge of feeding 10 billion people sustainably is not a distant problem for a future generation. It is our problem, and the clock is ticking. The limits of our current agricultural systems are becoming clearer every day. While quantum farming is not yet a reality on the ground, the foundational work must begin now. We cannot afford to wait. The journey requires a coordinated effort from governments, research institutions, the private sector. It requires a clear and ambitious roadmap to guide our investments and actions over the coming years, turning a scientific vision into a practical reality. First, governments must lead the way by significantly increasing funding for fundamental research. This means supporting the physicists and engineers who are building better quantum computers. It also means funding the interdisciplinary research that connects quantum algorithms to real-world agricultural problems, molecular simulation for catalyst design, quantum machine learning for genomics. Public investment signals the importance of the mission and de-risks the early stages of development, encouraging private sector participation. Governments should also foster international collaboration, because the challenge of food security transcends national borders. Second, our universities and research institutes must build the workforce of tomorrow. Break down the silos between academic departments, create new degree programs that combine quantum information, science, agricultural sciences, climate sciences. We need hands-on labs, internships, training programs that give students practical experience in applying these new tools.